So David Kelf from Breker Verification Systems, the Chief Marketing Officer, is going to speak about practical applications of portable stimulus. You may be seeing a theme developing now on portable stimulus. It is an important standard that's going to affect our industry and the way we do our SOC verification. David is a well-known EVA industry participant, having run the Cadence Verification Marketing, driven Synopsys Verification Strategy, and run marketing for co-design System Verilog, Novas, Verdi, and others. Now he's working with Breker on portable stimulus, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University. That's you.
Thank you. Who is that person? So thank you very much. So we've only got 15 minutes, so I can't get heavily into like this case study, but we wanted to sort of talk a bit about portable stimulus. You know, Accelera puts on a tutorial, which probably a lot of you have seen already, which gets into the language. What we wanted to try and do is just talk briefly about how it's actually used in some real designs. We picked a real case study here to talk about it a little bit. Before we do that, you know, a little bit about it, just in case some of you, haven't come across this. So portable stimulus is redesigned to tackle this problem of portability, particularly from sort of large block subsystem verification up to the SOC level and sort of integration testing, cache currency, those kind of things, and then into the early sort of software bring up kind of phase, with the idea that various tests can be created at one level, scenarios can be created at a high level, and then applied equally across all those different phases without having to be rebuilt. Mike actually talked about this morning a little bit, Mike Stelfox, so I won't go back over what he said. But essentially, what we've found at Breker is that on top of the general portability and the power there, we've actually been able to solve quite a lot of the trickier verification problems in the UVM space, the SoC space, and even post-fabrication silicon as well, which has proved pretty useful. A quick idea about what on earth portable stimulus is, you know, the really, really high level, probably a bit too high level explanation is, in the past, you know, you have to write UVM test sequences yourself in detail. What we're able to do with portable stimulus is kind of define a scenario. And a good analogy is an airline flight booking thing, which, where we define a scenario here like sending flights from San Francisco to Boston and back, which is something I have to do an awful lot. I don't use orbits anymore though. So you define this high level scenario, you set some constraints for a particular scenario you want to exercise for a particular set of tests, much like you would in a flight system. You know, I only want to fly United and Delta and don't want any stops and things like that. And let the system generate all the, in this case, possible flights, in the case of portable stimulus, possible tests that you then apply. So the idea is if we can create a high-level scenario, use random constructs at a very high level, set constraints for particular tests, we can generate a pretty broad set of tests which will tackle, you know, will find corner case situations and have better chance of discovering, you know, bugs that still remain in the system. In a real case, and here I've borrowed a graph from the Accelera tutorial, at a very high level, it can kind of look like this, where you take, in this case, the idea of texting a camera image in a cell phone. Basically, you would set up a very high-level test where you take the picture, you know, type in your text on a touchpad, lock the screen, and then, you know, the processor in the system actually puts this test together, loads it into memory, and then the final text message is put out either through one of the basebands, the LTE or the CDMA baseband. You know, very simple, but then each one of these boxes can be hierarchical, so you can start to build in information about the particular data that you're working with. For example, the photo image can be a JPEG or whatever. It can be a certain size. The touchpad can have a certain amount of text, so on and so on and so on. And then you can randomize all that. So you can build up a pretty comprehensive and powerful set of tests from this one simple scenario by just running through this path, particularly if this is hierarchical, which it would be. What does one of these graphs actually look like? This is a little bit hard to see probably from here, but essentially this particular one actually is an app that Breker provides, which tests a lot of things around an ARM V8 subsystem. And essentially each one of these yellow boxes is a hierarchical box with a series of tests underneath it. And in fact, one here, this is a graph which will analyze all the Moseley states, which is used in cache coherency in one of these ARM V8 subsystems. So you get a sense at this very high level, and a graph like this, you can actually capture a tremendous amount of information. And you can randomize all this and generate very high-level abstract tests. Okay? This actually, as I said, is an app. So what we're able to do is package up these graphs and make them configurable so you don't necessarily even have to write all the code that goes in behind this as well. I'm kind of tearing through this a bit, but all this is available on the website, and we can talk in much more detail offline if you guys are interested. Mike mentioned this earlier. The Celera has a committee which is standardizing or working on standardizing the portable stimulus standard. The committee has actually voted on a 1.0 version of it, which has been sent to the Celera board for ratification, hopefully by DAC. So that's what we're looking forward to now. And this is the same graph that Mike actually presented earlier. It's a Celera chart there. So I won't get into all the detail on that. Breker obviously is going to support this whole standard, as you would expect. In fact, we just announced it yesterday. And what does Breker do? Well, Breker takes the standard, takes this idea of creating scenarios, which we think of as basically executable specifications. In fact, you know, as Mike knows, I mean, because we've talked about this for many years, the holy grail of verification is this idea of creating an executable spec and then generating tests from it. And this really is the closest thing to it, I think, today. A clear spec that you can actually generate tests from. So the idea is you take this, you can synthesize a whole string of tests from this using the random solver built into the tools, plus all the different paths through the graph itself, and then deploy it into different situations. And that's really where I think it gets interesting. So, for example, a UVM block system, you know, for small UVM tests, portable stimulus is probably an overkill. But when you get to fairly large blocks or subsystems, you have a lot of ports you're trying to drive sequences into, the testing gets much more tricky. And if you're trying to generate sequences that go on multiple ports and synchronize them together, this can get pretty complex. So what we can do with portable stimulus is generate a high-level scenario model and use that as essentially a virtual sequencer to generate UVM sequences into an existing UVM test bench. Then you can do things like also generate scoreboards, coverage models, and this will be a coverage model that checks the coverage against the original scenario, and also put high-level constraints on this as well. So you can start to put very sort of high-level system constraints and have those translated down to lower-level random constraints for UVM sequences. So this is a pretty powerful idea. You know, a number of people are exploring this. When you get more to the SoC level, and now you're bringing processors into this, particularly for things like integration testing, like cache coherency, you know, power domain switching, which is the case we're going to look at in a sec. This kind of technology works really well. You can create a scenario. You can build that scenario from smaller scenarios. So you can take UVM tests and plug them into a sort of broader system-level test. And again, generate both software tests and transactions, synchronize the whole thing together. And then run these pretty powerful tests generated on this still straightforward scenario. And in this case, you're going to have various capabilities available, such as trick boxing, if you're familiar with that, you know, backdoor access to memory management, that kind of thing, which makes it very effective for debugging, etc. Okay, I'm kind of rushing along here, but to give you a sense of how one company uses this, and actually I can say now, when we actually gave you guys these slides, we didn't have permission to say who the company is, but since I got it, so it's Broadcom in Silicon Valley, and the team at Broadcom were basically had a system, a device, where they had a number of IP blocks that were processing data, and they had to process it in a specific order. So they were churning through this data, synchronized with these blocks, synchronized one after another, and they had an ARM M7 basically controlling the whole thing. And what they wanted to do was, while they were doing the functional tests, also cycle the power domains. And you know, this became a pretty complex thing to have to figure out, to try and generate all the different possible corner cases in this system. And the engineers there were trying to do this and write both C tests for the ARM processor and transactions on the blocks. They already had scoreboards and UVCs for UVM, and they wanted to sort of add the transactions into that. They had a fairly typical, I think, state machine for power domain cycling, and this is actually it. And basically, what this will do is depict how the power cycling would happen in a cold boot and a warm boot and so on. Again, for more detail on this, we can talk about it offline or it's on the website. This is a case study. So essentially, we set up a test bench which looked like this. It used a lot of the original UVCs from the UVM environment and the scoreboards as well, but essentially used the portable stimulus as a sequence generator and also C-tests for the processor, and we were able to synchronize the whole thing together. And what was nice is we were able to take the functional tests they'd already created in the graph, some of which actually weren't even in the graph, it was just a bunch of UVM sequences which we could bring in and use it with that, and layer on top of that the power cycling functional tests which we created based on that state machine you saw on the previous slide. And essentially, when we take that power state machine and build this graph to test this, to check the power cycling, the graph looks like this. And you can see it's not really that complex. It's pretty straightforward, and that completely describes the power cycling for all these blocks in this device. And essentially, the test went from a cold boot into a warm boot state. It then ran the functionality, which involved these different IP blocks working through the data in a synchronized fashion. So one had to process a certain amount of data before the next one, activate it, and so on and so on. And then, on top of that, layered on top, the power domains were cycled on and off at different points. And basically, by walking through the graph, the sequences that were generated could find all kinds of sort of interesting corner cases and things like that. And in fact, they did see some bugs by doing this. The nice thing about it, and where the engineers were having trouble, was trying to synchronize all these tests between the transactions on the hardware and the C tests on the software. And the system is able to do that because by looking at this high abstract scenario model and then generating tests, synchronizing happens just as part of that. This even got pretty complex because there were situations where the C test would be in memory, but because you might execute a warm boot or even a cold boot, the contents of the memory could be disrupted. But you had all your C tests sitting in memory, so how did you deal with that? And the system is actually able to put in traps to actually make sure that can be coped with as well. So it actually handles some of those things which otherwise have to be done manually, and they can be quite tricky. And this is a small set of the tests that are actually generated. You can see a number of different ports and the software tests. The software lines are in here, threads, sorry. And basically, these tests will be executed on that design and all synchronized together. So, okay, I'm almost there. So just to give a sense, a lot of people, I wanted to put this graph in because a lot of people say, well, portable stimulus is a new standard. We've got to wait for the standard to be executed. There's a lot of companies already using this. These are a lot of the companies working today with Breker. I know Cadence has a bunch of companies they're working with as well. So this is a live thing right now. It's very active. It's people are using this today and getting these kinds of results out of it. And it's pretty effective for a lot of these guys. Okay. And that's my since I haven't got any more time, that's my summary slide. Okay.
Thank you. Thanks, Lee.
Okay, great. Thanks.
We do have time for one question. If I can find my microphone. Thank you very much. Any questions? Yep, okay. And then we'll get our panel speakers ready as well, please.
What type of product is more suitable?
Sorry, what type of?
What type of product is more suitable for this portable stimulus? Mm-hmm. It's like wherever I see any presentation on portable stimulus, it's typically this is the standard set, but it might not be suitable for all kind of SoC, right? So
yeah, it's a good question. So I think where we've seen the sweet spots, it's large UVM tests, so not small ones, and not directed tests at the beginning of the process. Honestly, this is an overkill for that. So large UVM tests, and then the kinds of verification where you might be still working with a simulator or starting to use an emulator, and maybe more for an emulation, where you're doing things like integration testing, scenarios that do cache coherency and power domain type testing, testing the interrupts or connectivity in specific blocks, things like that. We have some companies who are bringing up Linux and trying to do testing like that. At that point, you're getting into the space which is more just general software testing, and I think you can use it for that, but that's sort of towards the other end. So I think the sweet spot is large UVM blocks right up to integration SoC type testing.
Okay.
But it pretty much works across all the emulators and all the simulators.
Right, thank you.